Thank you, Gus, for this great introduction, and thank you to all of you for showing up this morning. So what I plan to do today is to guide you through a journey of what I think are some of the most fascinating discoveries regarding astrophysical black holes. So I've chosen to structure this presentation around three main topics, that is to say, sharing some truths about black holes, debunking some myths about them, and then going into a more kind of research-oriented part of the discussion, what has to do with the main open questions about these extreme fascinating objects. So before I go into this kind of three-chapter talk, I would like to share some basic definitions as well as some historical notes that kind of take us back a century to the general theory of relativity, of which black holes are a fundamental prediction. So I'll start on a light note. Black holes have kind of a bad reputation. Many people tend to think about that as cosmic sinks that swallow just about anything that is around them. And to some extent, this is true, but I will try to show you that a great deal of good comes from this greediness. All right, so let's go back more than a century ago. In 1915, Albert Einstein publishes his general theory of relativity, which is a fundamental shift in the way to think about gravity. Up until then, Newton had taught us that gravity can be thought of as a force acting between two bodies that have a certain distance. The closer they are, the stronger the gravitational attraction between them. Einstein revolutionizes this concept and tells us that gravity is actually a geometrical property of the fabric of space-time, a quadridimensional surface, if you will, that you can think of more simply as a three-dimensional surface that in the absence of mass and energy is perfectly flat, but that in the presence of mass and or energy, which are the same thing, it curves. So represented here is sort of a cartoon to illustrate how even a relatively small, astrophysically speaking, mass, that is the sun, this is meant to be a depiction of the sun, creates a gentle curvature, a gentle saddle in the fabric of space-time. So curved space-time, tells us Einstein, is responsible for telling mass and light how to move, such that in the absence of curvature, light and masses travel on straight lines. But in the presence of a saddle, of a mass that curves space-time, they no longer travel on straight line. They travel on curved patterns, on what we call geodesics when it comes to light. So, one fundamental prediction of this theory is that masses that curve space-time will also bend light. So, fundamental prediction that was obviously revolutionary, and back then, many physicists and astronomers around the world took up the challenge and wanted to measure, to test and prove this prediction. So how to do that is fairly simple. So the idea is that if you could compare the position in the sky of a star in two different situations. One, say, when between us, this is Earth, and the star up here, this is our target star, in between, space-time is flat. So as far as this cartoon goes, when the sun is out of view, that the relative position of Earth and the sun are such that the star is aligned with our line of sight and nothing is in between. Space-time is flat. And then, if you could possibly do the same measurement when the sun is in the way, then at that point, the light coming from that star will be bent by curvature such that its apparent position, which is the projection of these lines, will be shifted by a certain amount. And for specific stars in the Hyades constellation, Einstein told us this displacement is about a little bit less than 2 seconds of arcs in the plane of the sky, which is about 1,000th of the size of the moon on the plane of the sky. So people take up the challenge. There's already a couple of missions that go out in 1914 before the final theory is published that are trying to follow a solar eclipse, a total eclipse, when the sun was eclipsed by the moon, such that you could do this measurement during the night. So when the star and Earth are such that the sun is not in the middle and the actual position on the plane of the sky is not curved by the sun. And then during the day, when the light from the sun is blocked, which you need in order to be able to see a star in the back, and test whether the expected displacement was indeed visible. So shown here now is the pattern of the total eclipse in the May 29, 1919 solar eclipse. 2 expeditions of British astronomers, most famously one of them led by Sir Arthur Eddington, set out to Brazil and to an island to the west coast of Africa to make this measurement, coordinated by Sir Dyson in the UK. And as you probably know, this was often referred to as the eclipse that changed the world. This is taken from a special cable to the New York Times dated November 10, 1919, which is effectively a little more than a century ago, that titles, "Lights All Askew in the Heavens. Einstein Theory Triumphs." Indeed, the displacement was measured and it was fully consistent with the prediction of the general theory of relativity. So mass and energy tells space how to curve, and curved space-time in turn tells matter and light how to move. So this works already for a relatively gentle curvature, which is that of the sun. Now, the more compact the mass we're talking about, the more extreme the curvature. And by compact, I mean the higher the mass to radius ratio it is. So the more mass you can pack within the same volume, the more compact you are, the more extreme the curvature of space-time will be. So again, in this cartoonish representation, up there you have the sun moving to a white dwarf, which is an extremely dense object, which has about the same mass of the sun, but the radius of Earth, down to neutron stars, masses of a couple of times the mass of the sun, a radius of 10 kilometers. This is about as dense as you can get while still having a physical surface. Past these kind of densities, you turn into a black hole. What's a black hole? Well, They're very elegant and sophisticated definitions that have to do with solving the equation of Einstein in expressing the metric of space-time. But in reality, the concept is very simple. Consider an object that carries so much gravity that not even light can escape from it, can escape from an imaginary surface whose radius we call the Schwarzschild radius, which in absence of rotation is the same as the famous event horizon radius. The expression of this radius is written here. G is the constant of gravity, c is the speed of light. This is an expression that derives from a very simple equality. Think of the amount of speed that you need to have to escape the gravity of a body in the most simple way, just a radial velocity escape from a body of mass m. And then you equate that with the speed of light, you get that expression. Anything whose mass is enclosed within this radius is a black hole. If you compress the sun to a radius of 3 kilometers, you make a black hole. If you compress Earth to a radius of 1 centimeter, less than half an inch, you make a black hole. If you compress yourself to the radius of a proton, you make a black hole. It's as simple as that, or not. All right, so now I've kind of set the stage for what the mathematical, if you will, notion of a black hole is. But really, I mean, does this exist in nature? Okay. Do black holes exist? And if so, what makes us think that that is the case? Right. Which brings me to chapter 1 here, facts. To the extent that science or the scientific process can be comfortable with truth, right? And by that I mean to say that we are always striving for a more perfect truth. So to the extent that we can tell, black holes do exist. They come in two main families. So shown here on this axis is the mass of astronomical black holes scaled in units of the mass of the sun. This is the kind of ruler that I will use for the rest of the talk. When we weigh black holes, we talk about solar masses, whether they weigh 10 times the mass of the sun or 100 times. And so they exist in two main families. This one we call stellar or stellar mass black holes. These have masses of a few times the mass of the sun up to a few tens times the mass of the sun. So about a few up to possibly 100 solar masses. Then there's a relatively big jump to a different family of objects that we call supermassive black holes. These, generally speaking, are referred to as black holes weighing millions to billions times the mass of the sun. To be fair, as Gus already hinted at, the gap is shrinking in that as we advance our instrumentation and become smarter about where to look, and we are finding more massive stellar mass black holes and less massive supermassive ones. But the question remains open as to whether, for instance, a black hole of 1,000 solar masses exists. There is no evidence for that yet. All right, so I told you they exist. Now I'm going to show you the results of two of the most, in my opinion, fascinating, groundbreaking astrophysical experiments in the last decade that prove, to the extent that is possible, the existence of a black hole. The first one is a relatively recent discovery, dates back to September 14, 2015, and it's the first detection by the Laser Interferometer Gravitational Observatory of gravitational waves from a pair of about 30 solar mass black holes that merged. As they merged, this event caused violent ripples in the fabric of space-time. Gravitational waves, again, a fundamental prediction of Einstein's general relativity. The idea is that in order for a gravitational wave to form, you need a time-varying asymmetric mass. In principle, even if I do this, I am a time-varying asymmetric mass, and I am emitting gravitational waves. Seriously. The fact is that the amplitude of those waves is minuscule, more so than the one I am going to talk about. And so, in order to even hope to be able to detect these waves that propagate at the speed of light and stretch everything that they pass through in very specific ways, including you, in this very moment, are likely being surpassed by gravitational waves that are propagating in all directions in the universe. So I have a movie here to illustrate how this works in the most extreme case that nature can think of, which is to say two black holes that start off with rotating around each other, around their common center of mass. They're losing orbital energy because they're emitting gravitational waves. And then when they come together, produce a burst in gravitational wave emission, and then settle to a more massive hole. So this movie is actually the result of numerical simulation work that is showing, so the underline kind of blue into green, here is the fabric of space-time that is curved by these very extreme masses. Each of these two things are 30-ish solar mass black holes. They're rotating around each other. Notice here time elapsing in seconds. This is in real time. Okay? As time goes by, and this will then slow down as we approach the merger, these two things are rotating around each other close to 30% of the speed of light. All right? And then here now the movie is going a little bit slower. You see these gravitational potential wells are merging. The movie is being frozen, and here is the so-called ring down phase, where this burst of gravitational waves is being emitted, propagates in all directions isotropically, and then on September 14, 2015, reached Earth and produced a displacement in two interferometers, one located in Louisiana, one located in Washington State, that measured this signal. These are two couples of L-shaped 4-kilometer arm lasers that worked like rulers, essentially the length of the laser L here. The measurement is of the so-called strain of the wave. This is a dimensionless quantity which expresses the ratio of how much that gravitational wave squeezed space-time and stretched that laser arm over the arm length. This number, you can read it up here, is in units of 10 to the minus 21. The amount of displacement that those lasers measured coherently, hitting the interferometers with a slight delay from between Washington and Louisiana, was of the order of 1,000 the diameter of a proton. So the kind of more ratty curve up there are the actual data is measured by the two interferometers, Hanford and Livingston. And underneath it, you can appreciate a more regular kind of weaker color curve. This is the model coming from numerical relativity, which fits. This is the combined model fit, showing as a function of time, see this fraction of a second, the in-spiral merger and ring-down phase of this black hole merger. And shown here in the bottom is the velocity as a fraction of speed of light. These objects were spiraling around each other at 30% of the speed of light, all the way to 50% of the speed of light. 150,000 kilometers per second. This is, as far as I'm concerned, the strongest evidence for the existence of astrophysical black hole, because the actual functional shape of this event in terms of amplitude variations as a function of time fits perfectly numerical simulations that are the results of general relativity. So this is stunning, and now I'm moving to another piece of evidence. So this is showing us the existence of stellar mass black holes in the range 20 to 30 solar masses. How about the big ones? Supermassive black holes. I believed if you were here a couple of weeks ago for Professor Megan Donahue talk, you might have seen this movie or a similar one. Now we are shifting to a different type of evidence. This is coming from staring at the very center of our own galaxy, okay, with very powerful, the most powerful infrared telescopes on Earth. In particular, this work is based on observations taken with the Keck telescopes on Mauna Kea in Hawaii. For of the order of 16 years, this team has been looking with very high cadence at this location. That star marks the position of a radio source known as Sagittarius A star, sits at the center of our own galaxy. Every little dot here is a star, at the position of a star. So as time elapses, this movie will show you the orbital evolution of stars around this one object. And I would like you to focus your attention on one special star, this one here, S2. Again, this movie is the result of real, actual observations collected over a period of more than 15 years. Time is up here. 2014, 15, 17, 18. So this yellow ellipse marks the elliptical orbit of S2. Why is it special? Because it happens to be the star that makes the closest passage, that goes closer to Sagittarius A star. Its period is of the order of 16 years. When it's closest to Sagittarius A star, its distance is measured to be of the order of 17 light years. Its velocity there is 5,000 kilometers per second. This is a star as massive as the sun, approximately, that's moving at 5 kilometers per second. Something down there needs to be sufficiently massive to support this motion. So the same way that you can actually measure the mass of the sun by knowing how fast the planets are going around it, such that they maintain equilibrium, they need to be moving sufficiently fast so as to not be swollen in, essentially, so they're on Keplerian orbits. You can do the same here, and the enclosed mass within those 17 light hours is 4.5 million solar masses. This is our own black hole. This is our own Milky Way galaxy, supermassive black hole, 4.5 million solar masses. All right, so I've shown you evidence for the existence of stellar mass black holes and supermassive black holes coming from wonderful instruments, one the LIGO interferometer, the other one Keck telescopes on Mauna Kea. Both these experiments, I wish to stress, are probing the existence of black holes thanks to their gravitational effects, dynamical effects. In one case by inducing ripples in the fabric of space-time, and in the other by measuring essentially the motion of stars around them. These are actually fairly exceptional experiments, and they require, particularly when it comes to this kind of dynamical experiments, enormous amounts of telescope time, not only, but you can only do this kind of experiments in the most nearby galaxies. In reality, by far and large, we know of thousands, tens of thousands, hundreds of thousands of black holes. In fact, we now believe that every galaxy has a supermassive black hole sitting at its center, and that every galaxy has millions of stellar mass black holes wandering around. And how we know that is actually, and perhaps counterintuitively, typically not thanks to these kind of experiments, but it's thanks to the light, the electromagnetic radiation that these black holes emit. So that brings me to the second chapter of these talks, myths. So the first one, you may guess where I'm going, is the following. Myth. Black holes are black. They aren't. In fact, I'm going to make the following statement that under the right circumstances, and by that I mean if they have some good amounts of fuel around them, and by fuel I mean gas. In fact, I'm not even going to be very picky. We need just a little bit of hydrogen around, protons and electrons floating. If there is a lot of gas, black holes are the brightest sources of light, of electromagnetic radiation in the whole universe. Now, I am cheating a little bit because the hole itself is black. It is the gas, it's the matter around it that emits enormous amounts of light. So how does that work? This process is referred to as accretion. The principle behind it is the very same principle that works in hydroelectric plants on Earth. All right? In that case, you take water from a certain height, you make it fall, and you're converting the gravitational potential energy of that water as it falls into kinetic energy, and in turn store it in turbines as electric energy. So your source of energy, your fuel, is gravitational potential energy. Now the statement here is that around black holes, around objects that have extreme compactness, this extraction of gravitational potential energy that I'm calling accretion is the most energy-generating efficient mechanism in nature. So here now I have my very high-tech demo. Newton's apple in a nut to Newton. So I'm going to make it fall. It does make a bit of a horrible sound, but bear with me. All right, I've got an apple. Can you guess what the mass of this apple is, approximately? 12 ounces. I'm a metric girl, so I'm going to go for 120 grams, but I think that's correct. All right, so I'll take it, and I make it fall. All right. Okay, so what I've done is to convert gravitational potential energy of my apple into kinetic energy, right? That's accretion. So imagine to do that in the most general case. You take an apple, make it fall from infinity instead of just, a couple of meters. The conversion of gravitational potential energy into kinetic energy in this case, on Earth, all right, given the mass and radius of Earth, as this amount of energy scales proportionally with the ratio mass over radius, if I could convert all that energy, all that kinetic energy into electric power, it would more or less power a light bulb, okay? Now I take the same apple, I'm not going to touch that one anymore. Take the same apple, imagine to do the same experiment with a black hole, all right? Now we are substituting, it's the same apple, same constant of gravity. You're substituting mass and radius for a black hole. Remember, the radius of a black hole, it's its horizon, which scales linearly with the mass. Well, the net effect is that you're generating 640 millions more energy from the same apple. So, in essence, accretion of mass onto astrophysical black holes, thanks to their compactness, is the most efficient energy-generating mechanism that we know of in the universe. It is 60 times more efficient than even nuclear fusion in the core of the sun. It also has an extra benefit. As this matter falls in and it gets heated by friction and viscous forces, it gets hotter and hotter and hotter and emits light in the optical, ultraviolet, all the way to X-rays. Okay, so it shines. This here is a computer simulation of an accretion disk of matter around a black hole. Now, the black hole is not producing this effect. This is just a simulation that is moving at the line of sight so that you're seeing it from different angles. All right? So the light emitted by this matter as it swirls in covers pretty much the entire electromagnetic spectrum. This is how we find these black holes. Once that matter crosses the event horizon, we can no longer see the light. We have this black hole in the middle. And the extra benefit that I was mentioning has to do with the fact that that mass goes into growing the hole. These things get more massive and more massive and more massive, so that if some of them are born at the beginning of the universe and keep swallowing mass in, they can grow to the masses of these monsters that we see today. And I will get back to this issue of black hole growth at the end of the talk. So, well, I've been showing you a couple of formulae that looks legitimate. and a computer simulation that looks cool, but how about the data? Is this seen in nature? And again, I think you know where I'm going if you have been following the press in the last couple of months. This probably reminds you of something you have seen. And so here we go. Again, one of the most groundbreaking and fascinating results in the last decade of astrophysics. I'm showing you a movie put together by the Event Horizon Telescope collaboration. We are zooming 50 million years away from Earth in the core of a galaxy called Messier 87, an incredibly massive galaxy that you're starting to see here, shown in optical and infrared light. All the images that you're seeing here are collages of actual astrophysical images. This is optical, optical again, radio, radio, infrared. This is the shadow or the silhouette of a 2 billion solar mass black hole sitting at the center of a galaxy 50 million light years away. For reference, the size of the hole inside the event horizon fits approximately the size of the solar system up to Neptune. Couple of things to mention. There is, I could give a whole talk about this image, but most notable are the fact that one side of this ring, which has been dubbed the ring of fire, is brighter. That is understood in terms of special relativity boosting of light. Remember, matter that close to the hole travels at a significant fraction of the speed of light, so the stuff that is swirling coming towards you and emitting light is going to look brighter. It has a higher frequency, electromagnetic frequency, than the one that's moving away from you. The same way the sound of an ambulance has a higher pitch when it's moving towards you with respect to going away. Exact same mechanism. So, hopefully, this has convinced you that black holes indeed exist. To be a little bit more technical now, here you're seeing the same event horizon image, the estimated size of the solar system that fits effectively into the horizon. And this here, this is a computer simulation that then gets fit to the data to establish the best fitting model, which, by the way, enables to infer that the black hole is rotating. This feature here is referred to as the photon orbit here. It's essentially a special location outside of the horizon where photons can go around in some quasi-spherical orbits before either escaping or going into their ultimate fate. One thing that you may notice here to the left is this depiction of something else coming out of this object. This is a cartoon, but the next slide shows you the real thing, and you already got a glimpse of it at the beginning of the video. So now we are zooming back out, going from the bottom right up. These are all images of M87 from the Event Horizon Telescope scales. This is fractions of a light years. 1,000th of a light years is this little teeny segment there. Zooming out to 1.3 light years down there, you're starting to see something highly beamed that at the largest possible scales looks like that. That is a relativistic jet, highly collimated beams of energy and radiations that are being powered by the black hole and pump energy and particles at extremely high energies into their surroundings. So my second myth has to do with black holes being cosmic sinks, cosmic vacuum cleaners. It turns out we don't really understand how, we have some ideas, they're capable of turning around a fraction of that matter that is going in out to relativistic velocities into their surroundings. One thing that is perhaps not evident from this image is the size of these things. The entire galaxy that hosts this black hole is 10 or 100 times larger than the Milky Way galaxy. And yet, it's smaller than these jets. The black hole down there is capable of powering these jets on scales that are much larger than the galaxy itself. And that is astonishing. Okay, one other small thing I would like to touch on before I go into the mysteries is this one here. People tend to think of black holes as incredibly dense objects. Now, this is not necessarily the wrong way to think about it, but it's not necessarily true either. It does depend on the actual mass of the black hole. This is because the mass density is the ratio, effectively, of the mass to the volume. But for a black hole, the size scales linearly with the mass, so that the mass density scales is inversely proportional to the mass of the black hole. In other words, the more massive the black hole, the lower the density inside its event horizon. I'm not talking about the density of the actual singularity. That will be infinite. So if you do the math here and put the actual constants in front and do the math, you can actually show that a black hole as massive as 140 million solar masses is as dense as water, which is to say it's as dense as you are. More massive black holes that we know of are even less dense. To the point that if you were to fall into that black hole, in the absence of matter that, as I said, is emitting X-rays, and so it would kill you, but forget about that. If you were just to fall into one of those, mathematically speaking, you wouldn't even know. You wouldn't know, because the tidal force, which is effectively a gradient in gravitational acceleration between your head and your feet as you're falling in, also scales with the inverse of the mass of the black hole to the second power, such that, you know, if you take a human of S would be your size, your height, of say 2 meters, you make it fall into a black hole of 140 million solar masses. The tidal acceleration, the difference in the acceleration between your head and your feet at the horizon, is less than g, is less the acceleration of gravity on Earth. You wouldn't even know. In contrast, though, because of this effect of inverse mass scaling, if you were to fall into a stellar mass black hole, 10 solar masses now, you'd be dead. This is because the tidal acceleration, not even at the horizon, 100 kilometers away from the horizon, is 50,000 times g. So you're done. Well, already quite a bit farther than that. So this goes in the so-called spaghettification. It's a highly technical term for tidal stretching. Okay, so in the last few minutes, I'd like to touch upon a couple of open questions. So I'm moving now into more of, in a sense, active research. I'm going to touch on a couple of issues that really keep theoretical astrophysicists, as well as observers, as I am, up at night and make us think about the next generation of instruments and experiments that we can think of to answer these questions. One has to do with the following. The plot is slightly technical, but the message is intuitive. So shown here, this graph has on the y-axis black hole mass. Again, this is in units of solar. But these are all supermassive black holes, 1 million, 10 billion, 100, 1 billion, 10 billion solar mass black holes. Every dot here is a black hole in its host galaxy. Remember I told you every galaxy has got a supermassive black hole at its center. So each of these objects is the image of the galaxy, but shown is the mass of its black hole. And now down here is a measurement of the average velocities of stars in that galaxy. So the more massive the black hole, the faster they move. And you might think, well, why should I be surprised? I told you that the star S2 around Sagittarius A star is moving at 5,000 kilometers per second because there is such a massive hole down there that supports that motion, essentially. So why is this a mystery? Well, the mystery is because these velocities measured on scales, on sizes in terms of the size of the galaxy, that are orders of magnitude larger than the area where the gravity of the black hole has any influence on anything around it, the gravitational sphere of influence. It's like saying that if the black hole gravitational sphere of influence is as big as a dollar coin, the velocity of these stars is measured on sizes as large as the larger Detroit area. This shouldn't happen. Stars down there shouldn't even know that there is a black hole. As far as they're concerned, where they live, space-time is perfectly flat. So why is this? And what it is telling us, well, this is interpreted as evidence for feedback. That is to say, these supermassive black holes, their evolution is intertwined with the overall evolution of their host galaxy, likely through those jets, to the extent that we think today that the very shape and color and size of galaxies is ultimately set by their nuclear supermassive black holes. Next, let's go back here. Where are the intermediate ones? Do they exist? And more importantly, these two questions are actually related. How do supermassive black hole forms? We don't know. We don't know. We know how the little ones form. Stellar mass black holes are the end product of stellar evolution. When there is a very, very massive star, nothing like the sun, something much more massive than the sun, once it runs out of fuel for nuclear fusion at its core, gravitational collapse will be unavoidable and lead to the formation of a 5, 10, up to possibly 100 solar mass black holes. This is very rare. There's plenty of evidence that objects like that exist. LIGO is starting to find the most massive of those objects. So aside from some details, this process is well understood. The problem is with the supermassive ones. They cannot possibly arise with those masses directly from stellar death. The record holder, kind of the lightest supermassive black hole, this is actually the Nature Astronomy paper earlier this year that my group was involved with, is at the very center of this galaxy here, NGC 4395, estimated to weigh 10,000 solar masses. At the other extreme, the current record holder is at the core of this galaxy. Don't be fooled. This galaxy is thousands of times larger than that. It's just much more distant, okay? And it's 40 billion solar masses. These cannot possibly form from stellar death. they must have formed through some other process, some global collapse of gas. Models tell us that in the very most optimistic conditions, you can form maybe a 100,000 solar mass black hole when the universe started to form the first galaxies during its first billion years of life. We are now at close to 14 billion years. So there's plenty of time to grow. Remember, if a black hole has enough fuel, it can accrete, it can swallow gas. So in principle, it's not a big of a problem. If you have enough time, if we wait enough time, even something that is born a few thousand solar masses or up to 1 billion can get to this, all right? There is a problem. There is a very hard limit to how fast you can grow these black holes. There is a limit to how much mass you can dump per unit time. And this is a very basic principle concept. So I said, if you wait long enough, you can do this. But this is what, and this is my last, well, not quite, my last scientific slide, let's say. If you squint your eyes, hopefully you can see a red dot there. Can you see it? Right. That is called Euler's blah, blah. That's his telephone number. That's a quasar, which is code for a supermassive black hole that is swallowing gas at very high rates. It's 2 billion solar masses. There is a problem. The light that you see there, that very red dot, that light was emitted when the universe was less than 0.8 billion years old. Has traveled to us for more than 12, 13 billion years. So that monster was already in place when the universe was in its infancy. There is no way to take even the most optimistic models for how massive a proto-black hole could have been at infancy and make it this large, this massive, that fast. This is a problem. And more critical, we don't even know if this is an exception, all right? There may be more of these. There may be some that are at even larger distances, which would make the problem even more critical. So I'm close to concluding with a word of optimism, which is to say, fear not. The future of black hole astrophysics is bright. There is a set of upcoming instrumentation that, among other scientific questions, are meant to address the question of how the first black holes formed. And I've selected a few here that are, I guess, in a sense, my favorite, or those that I think will make the most fundamental contribution to advancing our knowledge of black holes. Top left, the James Webb Space Telescope, the successor to the Hubble Space Telescope. After several delays, it will supposedly launch in March 2021. Its infrared capabilities are supposed to be able to detect objects like the one I showed you at farther distances and smaller masses yet. Down here, perhaps the most visionary and technically challenging of all, this is a mission that is led by the European Space Agency with a small NASA contribution. It's the Laser Interferometer Space Antenna, expected to launch in mid-2030s. This is taking the concept of LIGO, those 4-kilometer arm lasers that detect ripples in space-time, but put it in space with 3 spacecraft. Each arm is 2.5 million kilometers, trailing the Earth's orbit and aiming to detect ripples in space-time coming from merging supermassive black holes as opposed to stellar mass black holes. And last, this is something that I'm very proud to say the University of Michigan is a partner of, is one of the 3 concepts for an extremely large ground-based optical infrared telescope. Is the European ELT. Has started construction in the southern hemisphere in Chile. It will be, this is obviously a rendition of the project, will be a 39-meter class telescope with laser-guided adaptive optics that will be able to follow the motion of stars and gas and infer and weigh black holes the same way as we do in the center of our galaxy for tens and hundreds of galaxies in the nearby universe. And then, as I said, the Department of Astronomy at the University of Michigan is currently the only U.S. institution to have joined negotiations with 4 of the instrument teams that are building the instrument that will be retrofitted to this giant piece of glass. So to close again, the future is bright for black hole astrophysics, and thank you very much for your attention.